Our galaxy, like thousands others we have yet to discover, seems to have formed from nothing. Each one of these galaxies holds its own secrets and shares one big question: how did they come to existence? Join us as we explore the mysteries of the universe. The age of the universe is estimated to be approximately 13.8 billion years, a figure derived from a range of sophisticated observational data and theoretical models. This estimate is primarily based on the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, which provides a snapshot of the infant universe approximately 380,000 years after its inception. By studying the CMB and its subtle fluctuations, scientists can infer crucial parameters like the rate of expansion of the universe, known as the Hubble constant, which in turn helps pin down the universe's age. Another method involves observing the oldest known star clusters, particularly globular clusters, which contain some of the universe's oldest stars. By determining the ages of these stars through techniques like stellar nucleosynthesis, essentially examining the fusion processes that power stars, astronomers can set a minimum age for the universe. Additionally, the observation of the distribution and redshift of distant galaxies, as well as the intricate dance of cosmic structures governed by general relativity, all corroborate this 13.8 billion-year timeline. Through these interwoven scientific techniques and observations, we gain a coherent and remarkably precise understanding of the universe's age, revealing a cosmos that has been evolving and expanding for nearly 14 billion years. The Big Bang theory, which posits that the universe began as a hot, dense singularity roughly 13.8 billion years ago, is underpinned by several key pieces of evidence that together create a compelling narrative of cosmic origins. One of the most significant lines of evidence comes from the observation of the cosmic microwave background, CMB radiation. Discovered in 1965 by Arno Penzias and Robert Wilson, this faint glow permeates the universe and is remarkably uniform in all directions, with tiny fluctuations that reflect the initial density variations from which galaxies eventually formed. The CMB is essentially the leftover heat from the Big Bang, now cooled to just a few degrees above absolute zero and serving as a snapshot of the universe when it was only 380,000 years old. Another cornerstone of support for the Big Bang theory is the observed expansion of the universe, first noted by Edwin Hubble in the late 1920s. Hubble's discovery that galaxies are receding from us at speeds proportional to their distances implies that the universe is expanding. This was a groundbreaking realization that suggested the universe was once compacted into a much smaller, hotter, and denser state. The abundance of light elements, such as hydrogen, helium, and lithium, also bolsters the Big Bang model. Predictions based on the theory neatly match observed concentrations of these elements, which were forged in the first few minutes after the Big Bang as the universe cooled and protons and neutrons began to combine in a process known as Big Bang nucleosynthesis. These lines of evidence, combined with large-scale structure observations and the success of theoretical models in predicting various cosmic phenomena, create a robust framework supporting the Big Bang theory. Each piece, from the CMB to the expansion of the universe and the distribution of light elements, interlocks to tell the story of a dynamic, evolving universe that began with a tremendous explosion of space and time itself. The cosmic microwave background, CMB radiation, is essentially the afterglow of the Big Bang, providing us with a snapshot of the universe when it was just a few 100,000 years old. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this faint microwave radiation permeates the universe and is remarkably uniform, with minor fluctuations that reveal the density variations present in the early cosmos. These fluctuations are the seeds that eventually grew into galaxies and cosmic structures we observe today. The CMB is a relic from a time when the universe transitioned from being opaque and hot to transparent and cooler, allowing photons to travel freely through space for the first time. The study of the CMB has yielded a wealth of information about the universe's history, composition, and structure. For instance, Measurements of the temperature fluctuations in the CMB have helped determine the geometry of the universe, indicating it is flat. The CMB has also provided insight into the proportions of dark matter and dark energy, essential components that influence the universe's fate. The detailed maps produced by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have fine-tuned our understanding of cosmological parameters, confirming predictions of the Big Bang theory with stunning precision. This radiation serves as a cosmic blueprint, offering invaluable clues that help us piece together the grand narrative of the universe's origins and its evolution over billions of years. The formation of the first atoms after the Big Bang is a fascinating journey that unfolded during a period known as recombination, approximately 380,000 years after the universe's inception. Initially, the universe was an extremely hot and dense broth of quarks, gluons, electrons, and photons. As it expanded, it cooled down, allowing quarks to coalesce into protons and neutrons within the first few minutes, a process known as Big Bang nucleosynthesis. These protons and neutrons then combine to form the nuclei of the lightest elements, primarily hydrogen, along with helium and trace amounts of lithium. However, at this early stage, the universe was still too hot for electrons to bind with these positively charged nuclei to form neutral atoms. Instead, it was a plasma where electrons and protons existed separately, scattering photons and rendering the universe opaque. As the universe continued to expand and cool, it eventually reached a critical temperature of about 3,000 Kelvin, allowing protons to capture electrons and form neutral hydrogen atoms in a process called recombination. This transition had a profound effect. It decoupled matter from radiation, allowing photons to travel freely through space. These free photons make up the cosmic microwave background, CMB radiation that we observe today. With the formation of neutral atoms, the universe became transparent, marking the end of the Dark Ages and setting the stage for the formation of the first stars and galaxies. This profound phase change laid the groundwork for the complex and structured universe we see today, from the vast cosmic web of galaxies to the intricacies of planetary systems. The study of this epoch not only enriches our understanding of the universe's early stages, but also provides critical insights into the fundamental forces and particles that govern the cosmos. The large-scale structures of the universe are the grand, sprawling formations that define its cosmic architecture. These structures include galaxy clusters, superclusters, filaments, and voids, creating a vast and intricate cosmic web. At the heart of this web are galaxy clusters, which are massive groupings of hundreds to thousands of galaxies bound together by gravity. These clusters are often dominated by dark matter, making them gravitational beacons that play a crucial role in the dynamics of the cosmos. Galaxy clusters themselves are interconnected through even larger structures known as filaments. These filaments are vast strands of dark matter, gas and galaxies stretching across millions of light-years, forming the skeleton of the cosmic web. Between these filaments lie immense empty regions called voids, where very few galaxies reside. Superclusters represent some of the largest coherent structures and are conglomerates of galaxy clusters and groups. Our Milky Way, for instance, is part of the Local Group, which belongs to the Virgo supercluster, which in turn is part of an even larger structure called the Laniakea supercluster. The study of these large-scale structures provides essential information about the distribution and behavior of dark matter and dark energy. Observations reveal that these structures are not randomly distributed, but have evolved from tiny density fluctuations in the early universe, as evidenced by the cosmic microwave background radiation. Over billions of years, the interplay of gravitational forces caused these fluctuations to grow, resulting in the complex web observed today. This cosmic tapestry is not just a testament to the universe's vastness, but also a critical window into understanding its origins, composition, and ultimate fate. Cosmic voids, the vast empty regions punctuating the universe, form as a natural consequence of the gravitational evolution of matter in the cosmos. Initially, the universe was almost uniformly filled with matter, with slight density fluctuations present due to quantum perturbations in the early universe. Over time, these tiny fluctuations grew under the influence of gravity. Areas with slightly higher densities began to attract more matter, forming dense regions that would eventually become galaxies, clusters, and filaments. Conversely, regions with lower densities lost matter to their denser neighbors, gradually expanding and becoming more empty. As a result of this process, known as gravitational clustering, matter in the universe began to clump together, accentuating the density contrasts. Dense regions became denser, while low-density regions thinned out even further, leading to the formation of cosmic voids. These voids are not entirely empty, but contain very few galaxies compared to the surrounding filaments and clusters. The dynamics within voids are relatively quiescent, since there's less gravitational tugging from neighboring structures, allowing them to expand more freely as the universe itself expands. The study of cosmic voids is critical for understanding dark energy, the mysterious force driving the accelerated expansion of the universe. By examining the properties and behavior of voids, astronomers can gain insights into the overall geometry and expansion rate of the cosmos. Moreover, voids provide unique laboratories for studying the interplay between dark matter and baryonic matter, offering a clearer picture of the fundamental forces that shape the universe's large-scale structure. The observable universe is the portion of the entire cosmos that we can detect or observe from Earth, limited by the finite speed of light and the age of the universe. Light from the most distant objects we can see today has traveled approximately 13.8 billion years to reach us. However, due to the expansion of the universe, these objects are now much farther away than 13.8 billion light-years. In fact, calculations that account for the expanding space suggest that the radius of the observable universe is about 46 billion light-years. Astronomers measure the observable universe using a combination of techniques. One key method is the observation and analysis of the cosmic microwave background, CMB, radiation. The CMB provides a snapshot of the early universe, allowing scientists to gauge the scale and uniformity of the cosmos at that time. By studying the CMB's fluctuations and using the principles of general relativity, cosmologists can estimate the universe's size, shape, and rate of expansion. Additionally, redshift measurements of distant galaxies play a crucial role. The redshift phenomenon, where light from distant galaxies is stretched to longer, redder wavelengths due to the universe's expansion, allows astronomers to determine how far these galaxies are from us and how fast they are receding. These observations, combined with detailed models of cosmic evolution, enable astronomers to map the observable universe and understand its large-scale structure. This gives us a profound view into the history and development of the cosmos, though it is important to note that the observable universe is just a portion of the whole universe, which could be vastly larger and even infinite. The limits of what we can observe are set by both the speed of light and the time that has elapsed since the Big Bang, providing a cosmic horizon beyond which we cannot yet see. Estimating the number of galaxies in the universe is a monumental task, involving a blend of observational data, statistical analysis, and advanced technology. One primary method involves detailed surveys conducted by powerful telescopes like the Hubble Space Telescope, which can peer deep into the cosmos and capture images of distant galaxies in small patches of the sky. One famous example is the Hubble Ultra Deep Field, an image that reveals thousands of galaxies within a minuscule fraction of the sky. By extrapolating these findings to cover the entire celestial sphere, astronomers can estimate the total number of galaxies. Another crucial tool is numerical simulations based on the cosmological principles and known distribution of matter in the universe. These simulations model the formation and evolution of galaxies over billions of years, providing estimates of their numbers and distributions. By comparing simulated data with actual observations, researchers can refine their estimates, accounting for galaxies that might be too faint or too distant to detect with current technologies. Currently, the most widely accepted estimate suggests that there are about 2 trillion galaxies within the observable universe. This number might seem staggering, but it represents just a visible fraction of the entire cosmological landscape. Future advancements in telescope technology, such as the upcoming James Webb Space Telescope, will undoubtedly refine these estimates further and could even reveal previously unseen galaxies, continuing to expand our understanding of the vast and intricate universe. The Hubble Deep Field HDF image is one of the most significant achievements in observational cosmology, providing profound insights into the early universe and galaxy formation. Captured in 1995 by the Hubble Space Telescope, this detailed image focused on a tiny, seemingly empty patch of the sky located in the Ursa Major constellation. Over the course of 10 consecutive days, the telescope compiled hundreds of long-exposure photographs to reveal thousands of galaxies, spanning a variety of shapes, sizes, and colors. Some of these galaxies are among the most distant objects ever observed, offering a glimpse into the universe as it was billions of years ago. The significance of the HDF image is manifold. Firstly, it provided compelling evidence that the universe is filled with galaxies, even in regions previously thought to be devoid of significant astronomical objects. This discovery helped to shift our understanding of the universe's vastness and richness. Secondly, the diversity of galaxies captured in the HDF, including spiral, elliptical, and irregular forms, has offered invaluable data on the evolution of galaxies over cosmic time. Observing such a deep field has allowed astronomers to study how galaxies change and merge, shedding light on the processes that have led to the formation of complex structures like the Milky Way. Moreover, the HDF has fueled further astronomical research and observation strategies. Its success led to subsequent deep field images, including the Hubble Ultra Deep Field (HUDF) and the Hubble Extreme Deep Field (XDF), each pushing the boundaries of how far back in time we can observe. These images collectively enhance our understanding of the universe's early stages, the behavior of dark matter and dark energy, and the overall marvel of cosmic evolution. The HDF has thus had a lasting impact on both observational and theoretical astrophysics, continuing to inspire discoveries and deepen our appreciation of the cosmos. The expansion of the universe is measured primarily through the observation of distant galaxies and the phenomenon known as redshift. Edwin Hubble's groundbreaking work in the 1920s laid the foundation for our understanding of cosmic expansion. Hubble observed that galaxies are moving away from us, and the farther they are, the faster they recede. This relationship is encapsulated in what's now known as Hubble's law. The primary tool for measuring this expansion is the redshift of light from distant galaxies. Due to the Doppler effect, light from galaxies moving away from us stretches to longer, redder wavelengths. By measuring this redshift, astronomers can determine the velocity at which a galaxy is receding. To quantify this expansion, astronomers use a variety of calibrated standard candles, astronomical objects with known intrinsic luminosities. The most notable of these are Type Ia supernovae, which have consistent peak brightness and serve as reliable distance indicators. By comparing the observed brightness of these supernovae to their known intrinsic brightness, scientists can calculate their distances. When these distances are combined with the redshift data, it becomes possible to construct the relationship between distance and recessional velocity. More recently, the cosmic microwave background, CMB radiation, has provided another tool for measuring the universe's expansion. By studying the CMB, particularly with data from missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, cosmologists can infer various parameters that describe the expansion rate, known as the Hubble constant. Observations of the CMB's fluctuations allow for precise measurements of the universe's rate of expansion in its early stages, which can be compared with present-day measurements. These methods collectively give a coherent picture of the universe's expansion, revealing not only how fast the universe is expanding today, but also how this rate has changed over time. This data is crucial for understanding dark energy's role in accelerating cosmic expansion and provides key insights into the universe's past, present, and future dynamics. Dark matter is an enigmatic substance that constitutes approximately 27% of the universe, yet it remains unseen and undetectable by conventional instruments. Unlike ordinary matter, which interacts with light and can be observed through telescopes, dark matter does not emit, absorb, or reflect light. It reveals its presence through gravitational effects, warping the fabric of space-time around galaxies and galaxy clusters. This invisible scaffolding helps to explain why galaxies spin at such high speeds without flying apart, and how large-scale structures in the universe have evolved over billions of years. Detecting dark matter is one of the most profound challenges in modern physics. Researchers employ a variety of methods, ranging from observing cosmic phenomena to conducting intricate experiments deep underground. One approach involves looking for subtle gravitational interactions, such as the bending of light known as gravitational lensing, where massive objects like galaxy clusters distort the light from objects behind them. Another method involves direct detection attempts using highly sensitive detectors placed in mines or deep inside mountains to shield them from cosmic rays and other interferences. These detectors aim to observe rare interactions between dark matter particles and ordinary matter. Additionally, particle accelerators like the Large Hadron Collider search for signs of dark matter by smashing particles together at high energies, hoping to produce or detect dark matter particles. The quest to uncover the true nature of dark matter continues to be at the forefront of astrophysics and cosmology, holding the promise of unraveling some of the universe's most profound mysteries. Dark energy is a mysterious and pervasive force that comprises roughly 68% of the universe. Unlike dark matter, which binds galaxies together through gravity, dark energy is believed to drive the accelerated expansion of the cosmos. This concept emerged from observations in the late 1990s of distant supernovae, which revealed that the universe's expansion is not slowing down as once thought, but rather speeding up. To account for this unexpected acceleration, scientists hypothesized the existence of dark energy, a form of energy that permeates all of space and counteracts the attractive force of gravity on a cosmic scale. The influence of dark energy on the universe is profound and far-reaching. It affects the rate at which the universe expands, which has critical implications for its ultimate fate. If the current acceleration continues, dark energy could lead to a scenario known as the Big Freeze, where galaxies move so far apart that stars burn out and the cosmos becomes a cold, dark, and desolate place. Dark energy also impacts the formation and evolution of large-scale structures in the universe by working against gravitational collapse that leads to the creation of galaxies and clusters of galaxies. Moreover, dark energy may be linked to the cosmological constant, a term Einstein included in his equations of general relativity, which he later discarded as his biggest blunder. However, present-day cosmology suggests that this cosmological constant, representing a constant energy density filling space homogeneously, might indeed describe dark energy. The true nature and underlying mechanisms of dark energy remain one of the most compelling and elusive areas of research in cosmology, continuously pushing the boundaries of our understanding of the universe. The fate of the universe is a profound question that has intrigued scientists and philosophers alike for centuries. Based on current cosmological theories and observations, several scenarios could unfold, each dictated by the properties and behaviors of dark energy, dark matter, and the overall density of the universe. If dark energy continues to drive the accelerated expansion of the universe, a leading possibility is the Big Freeze, or heat death, where galaxies drift so far apart that star formation ceases, stars burn out, and the universe gradually fades to absolute darkness and near absolute zero temperatures. Another scenario, albeit less likely given current data, is the Big Rip. In this dramatic end, dark energy's repulsive force strengthens over time, eventually overpowering all other forces, tearing apart galaxies, stars, planets, and even the atomic fabric of matter itself. Alternatively, if the density of the universe were sufficient to eventually halt its expansion and reverse it, we might face a big crunch, where gravitational forces pull everything back together, culminating in a fiery, dense singularity. Each of these scenarios hinges on the nature of dark energy, which remains one of the greatest mysteries in cosmology. The ongoing quest to understand dark energy and its influence will ultimately help us unravel the destiny of our cosmos. Wormholes, as theoretical passages through spacetime, capture the imagination with their exotic possibilities, from instant travel across vast cosmic distances to even theoretical time travel. Albert Einstein and Nathan Rosen first proposed the concept in 1935, combining the principles of general relativity to describe what are often termed Einstein-Rosen bridges. These hypothetical structures could create shortcuts joining two distinct points in spacetime, potentially bending the laws of physics in mind-bending ways. However, the existence of wormholes remains speculative, as constructing or discovering one presents significant theoretical and practical challenges. For a wormhole to be traversable by humans or spacecraft, it would need to possess stability to prevent catastrophic collapse. This demands a form of exotic matter with negative energy density, a substance not yet identified in the observable universe. Such exotic matter would theoretically counteract the natural tendency of the wormhole's throat to pinch off and close. While certain quantum theories suggest that microscopic wormholes could exist at subatomic levels, any macroscopic counterparts are purely speculative at this point. Advanced mathematical models and extensive research into quantum gravity and other frontier sciences may one day provide more concrete insights. Until then, wormholes remain a tantalizing feature of science fiction and theoretical physics, showcasing the boundless possibilities birthed from the marriage of imagination and scientific inquiry. Black hole singularities represent one of the most extreme and enigmatic phenomena in the universe. At the very heart of a black hole lies the singularity, a point where matter is thought to be infinitely dense, and gravitational forces become infinitely strong. This concept emerges from the equations of general relativity, which suggest that under certain conditions, the collapse of a massive star can continue indefinitely, compressing all its mass into an infinitely small space. At this point, the known laws of physics no longer provide clear answers, and the curvature of spacetime becomes infinite. One of the most puzzling aspects of singularities is that they form a boundary of sorts, beyond which our current understanding of physics breaks down. Theories about singularities often lead into the realm of quantum gravity, where attempts are being made to reconcile general relativity with quantum mechanics. Physicists posit that to truly comprehend what occurs inside a singularity, a theory of quantum gravity is required, one that can account for the known forces at such extreme scales. Various hypotheses have been suggested, ranging from string theory's proposal of fundamental building blocks of the universe to loop quantum gravity, which reimagines spacetime itself as a lattice of discrete chunks, rather than a smooth continuum. The nature of black hole singularities continues to be a tantalizing mystery, setting the stage for future breakthroughs that may ultimately reveal the true workings of our universe at its most fundamental level. Studying the event horizon of a black hole, the boundary beyond which nothing can escape the gravitational pull, presents significant challenges primarily because light itself cannot escape from within it. However, recent advancements in technology and methodology have allowed scientists to make remarkable progress in this area. One of the pivotal methods involves observing the behavior of matter and radiation as they approach the event horizon. For example, matter falling into a black hole forms an accretion disk, heating up and emitting intense electromagnetic radiation, particularly X-rays and gamma rays. By studying these emissions with telescopes and space observatories, scientists can infer properties about the event horizon and the black hole's immediate environment. A groundbreaking milestone in studying black holes came in April 2019, when the Event Horizon Telescope, EHT collaboration, unveiled the first-ever image of a black hole's event horizon. This was achieved by linking together a global network of radio telescopes to form an Earth-sized virtual telescope, granting unprecedented precision and resolution. By capturing and correlating the radio waves from the vicinity of the supermassive black hole in the galaxy M87, researchers were able to generate an image showing the shadow of the black hole against the glowing backdrop of hot gas and dust swirling around it. The EHT continues to observe black holes, providing crucial data that help refine theoretical models and deepen our understanding of these enigmatic cosmic objects. Such collaborative efforts exemplify the extraordinary lengths to which humanity goes to unravel the mysteries of the universe using cutting-edge technology and international cooperation. Gamma-ray bursts, GRBs, are among the most powerful and luminous events in the universe, releasing in just a few seconds the same amount of energy the Sun will emit over its entire 10 billion-year lifespan. These intense flashes of gamma radiation are primarily classified into two types: long-duration GRBs and short-duration GRBs, each with different causes. Long-duration GRBs, which last more than 2 seconds, are thought to be caused by the collapse of massive stars, a process also known as a supernova or hypernova. When a star many times the mass of the Sun exhausts its nuclear fuel, its core collapses into a black hole or neutron star, while its outer layers are expelled in a massive explosion. During this collapse, jets of highly energetic particles are ejected at nearly the speed of light, emitting gamma rays as they interact with surrounding material. Short-duration GRBs, which last less than 2 seconds, are believed to result from the merger of two compact objects, such as neutron stars or a neutron star and a black hole. These collisions produce gravitational waves, detectable by observatories like LIGO and Virgo, and also release enormous amounts of energy in the form of gamma rays. The extreme magnetic and gravitational forces during these mergers generate conditions where gamma-ray photons are expelled at exceptional speeds, resulting in the bursts observed. The remarkable power of GRBs stems from the extraordinarily energetic processes that create them. The beaming effect, where jets of radiation are focused into narrow beams rather than being emitted isotropically, amplifies their apparent luminosity, making them detectable across vast cosmic distances. Studying gamma-ray bursts helps scientists understand the life cycles of stars, the formation of black holes and neutron stars, and the most extreme physical conditions in the universe. Ground-based and space-based observatories continue to monitor the sky for GRBs, contributing invaluable data to our understanding of these cataclysmic events. The concept of parallel universes or the multiverse is a tantalizing hypothesis proposing that our universe might be just one of many coexisting within a broader cosmic landscape. This idea emerges from several lines of theoretical physics and cosmology. One significant source is the interpretation of quantum mechanics that suggests every event splits the universe into multiple branches, each representing different possible outcomes. Known as the many worlds interpretation, this theory implies that countless parallel universes exist where every conceivable variation of events and histories unfolds. Another compelling notion stems from the theory of cosmic inflation, which posits that a rapid expansion of space-time occurred moments after the Big Bang. Some models of inflation suggest that this process could create bubble universes within a vast multiversal structure. Each bubble could harbor its own unique laws of physics and constants, making them independent and potentially very different from our own universe. String theory also entertains the multiverse idea through its landscape of solutions, where different configurations of extra dimensions give rise to myriad possible universes within a higher dimensional framework. While these theoretical models are intriguing, direct evidence for parallel universes remains elusive. The multiverse hypothesis challenges our ability to test it empirically, as interaction between these universes would likely be limited or non-existent under known physical laws. Nevertheless, cosmologists and physicists continue to explore the implications of these theories, leveraging advanced mathematics, simulations, and astronomical observations. The quest to understand if parallel universes exist pushes the boundary of scientific inquiry, opening new vistas in our search to comprehend the full scope of reality. The search for extraterrestrial intelligence, SETI, represents one of humanity's most profound scientific endeavors, aimed at answering the age-old question, are we alone in the universe? SETI primarily focuses on detecting signals or signs of technology from distant civilizations. One prominent method involves scanning the sky with radio telescopes to identify unusual or structured radio signals. These signals, unlike the chaotic noise from natural celestial phenomena, would ideally exhibit characteristics of artificial origin, such as narrow bandwidths, repeating patterns, or pulses at specific frequencies. One of the flagship projects in this quest is the SETI Institute's ongoing effort, using facilities like the Allen Telescope Array in Northern California. This array comprises 42 individual radio dishes, working together to survey vast swathes of the sky. SETI researchers carefully analyze incoming data, looking for anomalies that could signify intelligent life. In addition to radio waves, scientists have also expanded their search to include optical CT, which involves detecting laser pulses or other forms of light-based communication that might be used by advanced civilizations. High-powered lasers could potentially transmit signals across interstellar distances, making them a viable medium for extraterrestrial communication. Beyond dedicated SETI projects, astronomers are also exploring exoplanets, planets orbiting stars outside our solar system. The discovery of thousands of exoplanets, particularly those in the habitable zone where liquid water could exist, has significantly boosted the potential sites for intelligent life. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey satellite, are identifying these worlds, offering targets for future studies. In combination with advancements in technology, such as more sensitive detectors and sophisticated data analysis algorithms, the likelihood of detecting extraterrestrial intelligence, if it exists, continues to grow. The search extends not only outwards into the cosmos, but also encourages reflection on our place in the universe and the possibility of civilizations sharing the vast expanse of space-time with us. The Fermi Paradox, named after the physicist Enrico Fermi, encapsulates a profound and puzzling question in the search for extraterrestrial intelligence. Given the vastness of the universe and the high probability of many Earth-like planets existing, where is everybody? Despite the incredible number of stars and potentially habitable planets, we have yet to find any conclusive evidence of intelligent extraterrestrial civilizations. This apparent contradiction between the high likelihood of extraterrestrial life and the lack of observable evidence is what defines the Fermi Paradox. Several hypotheses have been proposed to explain this paradox. One possibility is the rare Earth hypothesis, which suggests that the conditions required for life, particularly intelligent life, are exceedingly rare and specific, making Earth an exceptional case. Alternatively, the Great Filter theory posits that there are critical and improbable stages in the evolution of life, and that most civilizations never pass through all these stages. This filter could lie in our past, indicating we are extraordinarily fortunate, or in our future, suggesting that advanced civilizations might self-destruct or face insurmountable challenges. Other explanations include the idea that advanced civilizations are deliberately avoiding us or have ethical reasons for not contacting less advanced species, often termed the zoo hypothesis. Another intriguing possibility is that such civilizations communicate in ways we do not yet understand, or are beyond our current technological capabilities to detect. It is also conceivable that intelligent life is so different from us that we fail to recognize it when we encounter its signs. While these hypotheses range from the pragmatic to the speculative, the Fermi Paradox continues to drive scientific inquiry and philosophical debate, pushing us to explore further and refine our understanding of life in the cosmos.